Okay, so finally we go on to geometric series with exercise 7D. So just to remind you, an arithmetic series was something like 2 add 3 add 5. And basically we get an arithmetic sequence and you add all the terms together. So you sum the terms. So a geometric series is going to be having a geometric sequence such as 2, 6, 18 and adding those terms together. Okay? So the key thing is you're adding the terms together to get a series, remember. Okay? So just stick this up there. So that's basically a brief recap of what the word series means. Okay? It's the sum of so many terms. Okay? So first of all, just like we did in arithmetic series, we're going to look at to see if we can find a formula for the sum of the first n terms of a geometric series. So the sum is going to be a plus ar squared plus ar cubed plus so up until you get to ar to the power n minus 1, until you get to the nth term. Okay? Now, what we did in arithmetic series was reverse the sum and then subtracted them. But with a geometric series, to eliminate all those number of terms in the middle that we don't know how many there are there, we are going to multiply our sequence by r. So we get a equals to ar equals to ar squared equals to ar to the power 3, and so on. So that middle group of terms there, if we subtract them from each other, will cancel out. So we'll be left, if I do s take away rs, I'm doing the top expression, take away the second one, I'll be left with an a. This stuff in the middle cancels, and I'll be subtracting ar to the power n. Now if we factorise the both sides, we'll get s brackets 1 minus r, and then on the right hand side we can have a brackets 1 minus r to the power n. So now if I divide both sides by 1 minus r, I've got an expression for the sum. So the sum would be a brackets 1 minus r to the power n divided by 1 minus r. Okay? Let's just move that across the left. Now if we had subtracted them in the opposite direction, so we'd done rs take away s, so the bottom one take away the top one, I'm not going to do that, but basically we would just get this. The r's and the 1's would be the other way around. Okay? So actually with geometric series we've got two formulae that we can fall back on. We tend to use this one, the green one, if r is less than 1. We use this one if r is bigger than 1, because then that would give us a positive number on the denominator, so it just gives us an easier formula to work with. But ultimately, if you use either one, in either context, as long as you're careful with your signs, they'll give the same answer. Okay, so let's have a look at doing some examples then. Okay, in this first example, we want to find the sum of the first 10 terms of the series 2 add 6 add 18 add 54. So let's work out what a is. That's going to be 2, it's nice and easy. R is going to be 3, because we're multiplying each term by 3 to get to the next one. Okay, n is obviously going to be 10. So because r is bigger than 1, I'm going to use this formula. So the one where we had r take away 1. So a brackets rn minus 1 divided by r subtract 1. Okay, so we're going to get our sum is going to be equal to 2 brackets 3 to the power 10. So because we want to find the sum of the first 10 terms, subtract 1 all over 3 subtract 1, and then just take that into a calculator, and that's it, done. This is such an easier formula to work with than the sum formula that you worked with in arithmetic series in core 1. So you put that into your calculator and that will give you the sum is equal to 59,048. Couldn't be easier. Let's do another example. Okay, I thought this next example we could just revisit what that Greek symbol means. Remember, it means the sum of r equals 1 to 8 of the series given by 2 times 3 to the power r. So what it means is I'd substitute 1, then I'd substitute 2 and 3 until I got to 8. So if we generate our sequence first, so we've got sum of r equals 1 to 8 of 2 times 3 to the power r. It's going to be 2 times 3 to the power 1, which is going to be 2 times 3, which is 6, plus 2 times 3 to the power 2, which is 2 times 9, which is going to be 18, plus 2 times 3 cubed, which is going to be 54, all the way up until we're doing 2 times 3 to the power 8, which would be 13,122. So we've got 8 terms there altogether. All we need to have is the common ratio, the first term, which by the way is 6. Common ratio, as you can see, like is 3. And n is equal to 8. So we stick that into our sum formula. So again, I'm going to use the one where I have r to the power n subtract 1 and r subtract 1 on the bottom, just because my r term is bigger than 1, just to make it easier. Again, if you use the other one, well actually try, alongside this video, if you try using the other formula, you should get the same answer. Well, you will get the same answer. So that's going to be 6 brackets 3 to the power 8, take away 1, all over 3 take away 1. So stick that into your calculator and you will get the following answer. 19,680. Okay? Easy. So one more example before you can get on with exercise 7D. Okay, so our last example then, we're going to find the least value of n such that the series 1, add 2, add 4, add 8, add to n terms is going to exceed 2 million. So this is similar to the ones that involved logs from exercise 7C. So we want to set up our sum formula. So we've got a is equal to 1, r is equal to 2. So therefore our sum formula is going to be a brackets r to the power n minus 1 divided by r subtract 1. So if we substitute our values for a and r into that, that's going to be 1 multiplied by 2 to the power n, subtract 1, all over 2 subtract 1. So therefore, if you simplify that, we'll have 2n minus 1. Just stick these up here, out of the way. So, that's our sum of those terms. So we want to find when 2 to the power n subtract 1 is going to exceed 2 million. So what we want to work out is 2 to the power n subtract 1 is going to exceed 2 million. Okay, so if we take the 1 across, that's going to give us 2 to the power n is going to be greater than 2 million. And 1. Okay. Let's just move that up a little bit. So then we're going to get, if we take the logs of both sides, we'll have log of 2 to the power n. It's going to be greater than log of 2 million. Okay. And 1, sorry. We can bring the n out of the log. So we've got n log 2 is greater than log of 2 million. And 1. I keep forgetting to say that number 1, don't I? So we want to do a quick check to see if log of 2 is positive or negative. Which, if you just stick that into your calculator, log of 2 is 0.301 blah blah blah. So it's a positive number, so we don't have to worry about changing that inequality. So we'll have n is greater than log of 2 million and 1, I remembered it this time, divided by log of 2. Okay, let's just drink that. These are all getting in the way a little bit now, aren't they? Let's just put these up there. So stick that into your calculator, and you will get n is greater than 20.93 ... So let's just stick that there. So therefore, we know that n is equal to 21. which tells us then that the first 21 terms will be the first number of terms that will exceed 2 million. If you remember, if you want to double check, you can stick n equals 20 and 21 into the summer formula up there. Okay, remember this is our sum formula. So if I stick 2 to the power 20, take away 1, and 2 to the power 21, take away 1, you'll see that it's the n equals 21 value is going to give you a number that's bigger than 2 million. Okay, so you can check that out for yourself if you want to. Right, that should be enough to get on with exercise 7D. There are some challenging questions in 7D, so get the easier ones out of the way so we can concentrate on the harder ones in class. Good luck.